All right. In the last lecture, we saw how we can use Taylor polynomials to approximate a non-polynomial function near a given point. And we saw that as we add more and more terms to a Taylor polynomial, it improves the approximation near that point. And so we might ask ourselves, well, what happens if we just keep adding terms to a Taylor polynomial? Can we model the whole function with a Taylor polynomial? How good is our approximation? How far out can we go from that point that we're modeling around and have it still be a decent approximation? So in this section, we're going to start answering some of those questions. We're actually going to cycle back to Taylor series at the end of the course once you have a few more tools in your tool belt to be able to analyze those questions. But for this lecture, we're just going to sort of introduce the idea of Taylor series. So a series in mathematics, a series is if you add up an infinite number of terms, we call it a series. And so you can see these two formulas that I have here are basically the same formulas that we used last time for Taylor polynomials, except that there's a dot 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 indicating that they were just going to add an infinite number of terms. So we obviously can't write an infinite number of terms, so we just use a dot 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 just to say the pattern continues. And you can see we also have a general term, which would be our nth term, but we're just going to keep adding. We're going to go beyond n and just keep adding terms. All right, so this first example is just to find the Taylor series for e to the x around x equals 0. Okay, so now rather than a Taylor polynomial, we're finding a Taylor series. And there's not a whole lot new in this section. If you can write a Taylor polynomial, you can write a Taylor series. All you need to do is put dot 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 at the end. And you've got it. So let's take a look at this. Now, I know we did this. This was actually, there was a example 4 in the last lecture, was to write a Taylor polynomial for e to the x. It might have been the 7th order Taylor polynomial. Now we're going to write a Taylor series. So, but we need essentially the same information. We need f of 0, right? F of 0 is just going to be 1. And then we need the derivatives, right? So we're just going to use these formulas up here. So we need the derivatives of e to the x at, we just need to, first of all, start with the derivatives. And the derivatives of e to the x are really simple, right? Because the derivative of e to the x is e to the x, so the first derivative is e to the x, the second derivative is e to the x, e to the x, and so on. The third derivative is e to the x. Okay. So if we evaluate those derivatives at x equals 0, right, then we just get 1, right? So any of these derivatives, all of these derivatives at 0 are equal to 1. All right, so now we have the information we need to write the first 3 terms, at least, or actually 4, right? Because we have the 0th term. So f of x, just like we wrote the Taylor polynomial, is equal to f of 0, right? We're just going to use this formula. So put in 1 plus 1 times x, right? Because the first derivative is 1, so 1 times x, plus f double prime, which is 1 over 2 factorial x squared. The third derivative at 0 is 1, so it's 1 over 3 factorial x cubed, and so on. All right, and we just put dot dot dot, and it becomes a Taylor series. That's exciting, right? So nothing new here. Now, one thing that is a little bit new is we might be asked to find the general term of this Taylor series. So that's a little bit of a trick sometimes. Now, you can kind of see the pattern. What you're doing is basically looking for a pattern, and you want to be able to write an expression for the nth term in terms of an integer k. And so you can see a pattern. We have 1, and you could write this as 1 over 1. We have 1 over 2 factorial, 1 over 3 factorial. This could be 1 over 1 factorial. Now, you might also, we kind of called this the 0th term. So you might recall that 0 factorial is also 1. So we can actually write our series like this, and then you can see a nice pattern happening with these coefficients. So we could actually write the kth term of this series as 1 over k factorial x to the k. Now we need to define what k is, because we're starting with 0. So if we define our kth term this way, then we're starting with k equals 0, and then 1 and 2 and so on. All right. So whenever you write the kth term, you have to define how you you need to specify how you're defining k. So because you can write this another way too. If we wanted to start with 1, and 2 and 3 and do it that way, we'd have to subtract 1 from k, right? So this would be k minus 1 factorial x to the k. Okay. Make sure if you've got a k minus 1 factorial like this, where you put parentheses around the k minus 1. Otherwise, it just looks like 1 is to the is factorial and not the whole thing. But we could write our kth term either one of these ways, depending on how we define k, right? So probably the simplest though is just to let k start with 0, and then you can write it the simpler way, the first way. All right. So that's it for the first example. I would encourage you to go ahead and look at the second example and try it on your own. But I'll meet you in the next video for example 2.